All right, so continuing on with the chapter 5 slides, we had just ended up talking about endothermic and exothermic in the last video. We're going to define some more terms here as we get closer to the math side of things that we want to consider here. So we'll talk about what mechanical work looks like in a chemical system, and then we'll define a new parameter, enthalpy, which will be more directed towards what we're interested in talking about. Before that, we want to define what a state function is. And understanding a state function will help make better sense of our general approach to quantities that we're thinking about, and how we're focused on the change in values rather than the actual values. So when we talk about a state function, primarily what we're talking about is something that is path independent. And so the example here is to say, if I told you I had a system that contained 50 grams of water at 25 degrees Celsius, that would be all the information you really needed to know to describe that system, right? You wouldn't need to know if I cooled down hot water to get to that point, or if I melted ice to get to that point. That wouldn't matter, right? We would just say, knowing that it's 50 grams of water at 25 degrees Celsius, that fully describes the system. So that would be something that we describe as being path independent, right? It doesn't matter how I got to that condition. Now I am able to fully describe it. So with regard to the internal energy, we would say the internal energy of a system is independent of the path by which the system achieved that state. So going back to this original example, it doesn't matter how our water reached this state. We still understand the internal energy and how to calculate the internal energy. So anything that's path independent is referred to as a state function. And it only depends, the reason it's called the state function is because it only depends on the present state of the system, not on the path by which the system arrived at that state. So what that means is, if I know E initial and E final for a system, that's all the information that I need to know. And therefore, if I figure out delta E, that's telling me, regardless of the path followed, that's telling me the change in internal energy that has occurred. And then I can use that to understand the ways in which heat flow and mechanical work may have changed as well. So remember, our kind of mathematical approach to thinking about the first law is to say any change in the internal energy of the system is caused by some combination of heat flow and mechanical work. So how the internal energy changes doesn't matter, but that means that E is a state function, but Q and W are not state functions, right? Some amount of this change could be heat flow, some amount of it could be mechanical work, but they are not state functions. So in the picture here, in diagram A, we've got a battery hooked up to a heating coil, and that battery is discharging by giving off heat through that heating coil. On the right-hand side picture, we see that our battery is in line with a fan, and so the primary usage of the energy as that battery discharges is to turn the blades of the fan, which would qualify as mechanical work. But the battery is still going to lose some of its energy just through the wire as it travels in that system. So we're saying in each case, imagine we started with a charged battery and we got all the way to the discharged battery, then that would mean its internal energy change is the same, but Q and W are going to be different in the two cases. So that's an important thing to talk about, right? The internal energy change could be the same from state A to state B, but what fraction of it comes from heat flow and what fraction of it comes from mechanical work, that could vary from one case to the other. So for that reason, we'd say the internal energy E is a state function, but the heat flow Q and work function W are not state functions. So in that example, what we saw was a battery connected to a circuit basically with a fan on it, and so some of the energy being used up as the battery discharged, or hopefully the majority of the energy, was to turn the blades of the fan. So that should lead us to a reasonable question that you may have had earlier on, which is just, why do we talk about mechanical work when we're thinking about chemistry? What does mechanical work look like in a chemical system? So the best example for that is to have a container with a movable piston. So typically a gas sample in a cylinder like you see here with a movable piston. So this piston is able to be moved depending on what pressure exists on the outside and what pressure exists on the inside. So in this case, what's kind of in orange or red, that's our system, and it's pushing outward against the piston. So what we're observing in this particular case is an expansion, right? The system, whatever its gas contents are, the system is pushing out against the surroundings. So remember, when we first talked about work, I kind of gave the example of sliding a mass across a surface, and there was some frictional force that was counteracting our ability to slide that mass across the surface. Well then, in this movable piston, it's kind of the same idea. Now we're pushing this piston outward against atmospheric pressure. So that's our counterforce to pushing it outward. So in that regard, it should make sense how this picture of pushing out against a piston should qualify as mechanical work in much the same way sliding an object across a surface would be. So in this case, the vocabulary we would use is we'd say work done is by a gas pushing on the surroundings. So if it's an expansion, that means work is done by the system on the surroundings. Work done by system. So let's specify this vocabulary for both cases, the expansion and the compression, and see how it works out for our W value. So the equation, right, remember that the equation for work in a simple model is work equals force times distance. Now we're saying work equals negative external pressure times the volume change. The reason for the negative sign is that so we appropriately describe whether the system is using up energy or whether the surroundings are using up energy. So having this negative sign along with delta V, that coincides with what we were saying earlier. That means if delta V is positive, work will have a negative sign. If delta V is negative, work will have a positive sign. So we'll elaborate on that in just a second. This particular picture here is describing a reaction, zinc metal plus 2 HCl, AQ means dissolved in water, makes zinc chloride plus hydrogen gas. And zinc chloride also dissolves in water. So in this picture, we've got some zinc metal, and we dump it into our aqueous hydrochloric acid solution, and as this equation describes, the hydrogen gas that gets produced is going to find its way up to the piston, and then what you see in the later picture is it substantially pushed the piston outward. So we want to understand that to be work being done by the system on the surroundings. So delta V is positive, meaning the sign for W is negative, to indicate the system is losing energy as it performs work on the surroundings. So this is where we are, right? If the volume increases, delta V is positive and therefore W is negative. In this case, we would say work is being done by the system on the surroundings. And that makes sense, right? Gas generated in the system is pushing this piston outward farther into the surroundings. If it were the other way around, which it is not in this case, but if the volume decreases, then delta V would be negative. Given that there's already a negative sign in the equation, work would be positive. So now I would say work is being done on the system by the surroundings. So expansion is the system doing work on the surroundings. Compression is the surroundings doing work on the system. So whichever one is pushing is the one that is doing the work. And so there are examples of reactions like this where we're producing a gas and pushing outward. So there is a mechanical work portion to the internal energy change. Generally, we don't need to consider this unless we're in a unique situation. So what we'll see going forward is we'll kind of agree that primarily internal energy change is going to consist of heat flow in a chemical process. So we're going to simplify our approach just to think about that. But since it is possible for mechanical work to be part of a chemical system, I just wanted to make sure we talked about how that could be the case. So, as I said, our goal is to kind of simplify things, and it's not going to look like we're simplifying things initially, but it will turn out that way. So, we're going to introduce a new term called enthalpy. And mathematically, enthalpy is defined as the internal energy value plus the product of pressure and volume. But what we're going to see is that primarily our chemical processes are just going to involve heat flow. So we're just going to focus on heat flow by measuring this quantity called the enthalpy of the system. So the way in which this quantity is defined, H equals E plus PV, that's important, but it's defined mathematically so that terms cancel out, so we end up being able to focus on what we really want to focus on. So it doesn't matter if you know that H equals E plus PV, it's more important to say that enthalpy is going to correlate with a constant pressure process, and in parentheses I wrote, as the majority of processes we study do, and therefore the only work done is pressure volume work. So then enthalpy will just account for heat flow at constant pressure. So that's really the way we want to define this. Let me write it here. I think it says this a little bit later, but so if you think about it, right, if I just have an open reaction flask and I'm interested in heat flow as it is happening in my reaction, that would be enthalpy, right? Because the pressure outside is constant. So if it's an open flask, then any heat flow within that flask to the surroundings, that would qualify as enthalpy. So the second bullet point here, like I was saying earlier, that's just to make the math work, and we'll see that in just a second here. So we said enthalpy equals internal energy plus the product of pressure and volume. So then if I take the change in all of those quantities, it'll be delta H equals delta E plus, or delta parentheses E plus PV. So this would really work out to be delta E plus P delta V plus V delta P. When I'm doing the change in the product of two quantities, that's the way that it's going to break up. But since I'm at constant pressure, delta P equals 0, so V delta P drops out of the equation, and then I get this equation instead. Delta H equals delta E plus P delta V. So that's how we're defining the enthalpy change for a process in terms of the internal energy change and the volume change. So now we're going to do a simple substitution, or two simple substitutions, I guess. First, we know delta E equals Q plus W, so the delta E term in our enthalpy change expression, I'm just going to replace with Q plus W. And then separate from that, we know work equals negative P delta V. Well, I have plus P delta V, which is really minus negative P delta V, or minus work. So, like I was telling you in the beginning, the enthalpy term was defined in such a way that terms would cancel out, and we get this expression. So this goes back to what I think I said earlier, which is just that if we're at constant pressure, the change in enthalpy is the heat gained or lost. So under standard conditions, the enthalpy change is equal to the heat flow. So that was a lot of kind of manipulating a mathematical equation to get a result that I already told you, but that's what you want to be able to say when you come out of this is whenever you hear enthalpy change, it's talking about the heat flow. It does say the heat flow at constant pressure, but that's almost always going to be the case unless we're in a sealed vessel, which we don't really talk about stuff like that very often. So then now we are correlating the enthalpy change delta H with Q. So that's going to allow us to connect the endothermic, exothermic terminology with the enthalpy change. So a positive enthalpy change is going to result in an endothermic process, and that still corresponds to endo being inward, heat flowing from the surroundings into the system. Then on the other side of this, a process is exothermic when delta H is negative. And so that means heat is flowing out of the system into the surroundings. So same thing with our knowledge now that delta H, the enthalpy change, is the same as the heat flow at constant pressure. We can correlate these to this terminology. So delta H positive, endothermic, delta H negative, exothermic. So let's see, what else is there to say about the enthalpy of the reaction or the enthalpy change of the reaction? It's still talking about a delta value, so the change in something. When we're talking about a reaction, when we want to think about the change, rather than final minus initial, it's going to be product minus reactants. So if I know the enthalpy of the products and the enthalpy of the reactants, then the change is simply the difference between those two, products minus reactants. All that really means for us right now is if I know the enthalpy change for a reaction in one direction, then that tells me the enthalpy change for that same reaction in the opposite direction is the same numerical value, but with a sign change. So one of these reactions, the combustion of methane, is releasing 890 kilojoules, but if we reverse the reaction to combine carbon dioxide and water to make methane and oxygen, methane is CH4, then that's going to cost us 890 kilojoules. So that's something to think about with regard to enthalpy of reaction. And so And we should always say enthalpy change, but you'll also hear enthalpy of reaction, but it still should be describing a change. So delta H can be called the enthalpy of reaction, the enthalpy change of reaction, or I think because it's an H, there are a lot of times we just call it the heat of reaction, but those things are interchangeable. Okay, looks like this picture down below is showing the actual hydrogen and oxygen reaction where we bring a flame in close contact to our hydrogen balloon in the presence of oxygen, and we get to observe the actual combustion of hydrogen. So same story here. If I knew the enthalpy change delta H for this reaction in one direction, then I know the enthalpy change in the opposite direction is the same numerical value, just with the sign swapped. So enthalpy, we haven't used this term in a while, but enthalpy is certainly an extensive property, right? The more stuff that goes into a reaction process, the greater enthalpy change we're going to observe. And then as we said, if I know the enthalpy change in the forward direction, it's equal but opposite to the enthalpy change in the reverse reaction. And a third point, which I think won't come up until probably chemistry 2, is that the enthalpy change itself does depend on the state of the products and the state of reactants. So whether things are solids or liquids or gases, that's important to think about as we look at this. So enthalpy is going to set us up to have a very brief discussion about the idea of calorimetry, where we find different ways to measure heat flow for certain processes. We're not going to do that for actual chemical reactions. Again, that's something saved for the second semester course. But we are going to talk about the ways in which we can use calorimetry in order to figure out heat flow associated with a process. So that's the way we get these enthalpy change values, is by conducting reactions in an insulated vessel like a calorimeter, and then finding a way to observe the heat flow in that particular process. So I think we'll pick up with this slide here. It looks like it's 37 in the next video, and then in that next video we'll wrap up this chapter 5. So I think you should now be in position to do all of what I called chapter 5 homework number 1. It's through slide 35, so we've covered all of that now, and then after the next video you should be able to handle the rest of those problems as well.